For drug discovery, I think a big bottleneck is actually in making the drugs. So if you're a pharmaceutical company, I think you can keep the computer running and generate billions of molecular designs, but probably your wet lab can only afford synthesizing, a small handful of those.
Maybe also if we can expand into like VQE, it's like variational quantum eigensolver, or now it's like variational quantum algorithm. Maybe if you could explain about how it works and what are the other competing solutions for chemistry, let's say for quantum computing. Also, maybe we can mention the classical, such as density function theory. What is maybe the like pros and cons, just like a brief overview of the field of computational chemistry.
I mean, computational chemistry is concerned about calculating the properties of atoms and molecules. And there are two kinds of properties generally. There's a static property, for instance, the energy levels of a molecule. So these energy levels tell you something about, for instance, what kind of light it tends to absorb, or how much energy does it take for it to react with another molecule, for instance. So they tell you important information about the behavior of the molecule, but they are also incredibly difficult to compute because what drives these energy levels is the behavior of the electrons in those atoms and molecules. And the way of quantum physics is such that the amount of information you need to keep track of regarding those electrons typically blow up very quickly the more electrons you add to it. So very quickly, the classical computers at least gets overwhelmed with the need to keep track of the possible states of the electrons. If the goal is to calculate these energy levels to perfect accuracy. So that was recognized very early on, like in the early days of quantum mechanics, that there's this exponential blow up. But remarkably, there are ways around it where it seems that with enough insight, you can find an answer that's close enough. So much of quantum chemistry, much of computational chemistry in the past decades have been dedicated to finding methods that can give you approximate solutions to these incredibly difficult quantum problems. So some of the examples are, like you said, density functional theory, DFT, and there are other methods like coupled clusters. I remember working, when I was at Harvard, working with quite a few co-authors on compiling this review article where we try to map out the landscape of computational chemistry problems. That was a very useful learning because it really shows what are the intersections between computational chemistry as people have worked on it in a classical computing world and quantum computing, which is this new way of thinking about computational chemistry. One very high-level thing to mention, because there's an incredible amount of technical details. One interesting high-level thing that I've learned is that it seems that quantum computers allow you to do things that are big no-nos for computational chemists. So in computational chemistry, it's a big no-no to write down the entire electronic wave function because that's the object that will exhaust the memory of even the largest supercomputers in the world for even molecules that are moderately large. Much of the computational chemistry on a classical computer is to think about how to avoid writing down the whole wave function, how to get away with just the smallest amount of information that you need to describe the wave function and then try to update it in a clever way, maybe take advantage of the structure of the molecule, maybe take advantage of some of the formalisms in quantum mechanics. So there are all kinds of clever ways to avoid writing down the wave function.
Clever shortcuts.
Right, yeah, clever shortcuts. But with quantum computer, the very point is to essentially write down the wave function. If you can generate a quantum state on a quantum computer that somehow encodes the state of a molecule, then you're essentially writing down, right, quantum mechanically writing down the wave function of the molecule. And that is something that's very standard in quantum computing called state preparation. It's a very basic thing in quantum computing, very natural thing. But for classical computing experts working on computational chemistry, this is very unthinkable. So that's one interesting thing. And another interesting thing was that time evolution of the wave function. So take Schrödinger's equation and just brute force populate the wave function over. So this is essentially requires taking this exponentially long vector and then operate on it with an exponentially large matrix to figure out, for instance, what's the state of the electron after a certain period of time. This is also something that's doubly expensive. So if it's already expensive to store the wave function, then trying to do a matrix vector multiplication is going to be doubly expensive. So this is, again, something that computational chemists would never even dream of doing. I think that there are clever workarounds. For instance, with tensor networks, there are methods on classical computer where you can have a very succinct description of the wave function and then find clever ways to update it such that at least for a short period of time, you can keep track of the state. But after a certain period of time, you start losing accuracy because the classical computer is not storing the whole wave function. It's an approximation. So there are things like that.
Is it more for classical computers the problem of memory? So it's a memory limit, but not the processing power limits?
I think it's a bit of both. I think memory is really the first order problem. There are ways to compute in place, like without having to store the entire wave function. So then in that case, it becomes a compute bottleneck. Essentially, for classical computers, doing quantum chemistry calculation in its full accuracy means that you need to chuck through exponential amount of, basically, you could store that all in once on the computer and chuck through it, or you can somehow do this in-place computation. But regardless of what you do, it's still an exponential amount of information processing. But with a quantum device, you can generate a quantum state which itself is already this complex quantum mechanical object, and then perform measurements and operation on it in ways that are likely very difficult for classical computers to do it, because classical computers have this exponential overhead. So that's essentially the inspiration for this variational quantum algorithms. The idea being that you can take a quantum computer and generate some quantum state on it. You can take qubits, initialize them, and then perform some operation, and then get the qubits into this potentially very complex, highly entangled state, and then perform measurements on the state to obtain information. So all of that process is very difficult to replicate on a classical computer. And the inspiration for this variational quantum algorithm is to exploit this process and to see if you can actually do something that is beyond what classical computers can do. That's the basic idea of variational quantum algorithms. And then one specific example that, at least when Zapata first started, we're very excited about it, was this variational quantum eigensolver, which is naturally to say, if you can have a quantum computer that prepares a quantum state that encodes the ground state of a molecule, then by directly measuring on the quantum computer, you can get the energy value of the molecular system directly. So this is a shortcut to a shortcut to classically trying to find out the ground state energy by these exact methods, essentially.
When I look at the variational quantum algorithms, I basically see that it would be true to say that the quantum circuit essentially is the way to probe the space of the possible solution. So it provides like a new bootstrapping of this infinitely large Hilbert space of the wave functions. And then the rest is just computation of the integrals and retrieving the eigenvalues, and then just trying to find, let's say, ground state of the molecule by minimizing the value of the energy. So you just go one by one in terms of getting the wave functions, plug it in, compute, and then compare, and then find out just which one gives you the minimum energy value. Is that, or there is something more in VQA than just processing the probing the space of the wave functions?
Right. Yeah, I mean, VQA is essentially, I think a good analogy is just training neural networks. So VQA is like training a quantum a quantum function. So if a neural network is just a tunable function where you train with data to learn a certain mapping, the same thing with VQA, except that now this, instead of a neural network running on a classical chip, you're running this quantum process with tunable knobs on a quantum computer. And the idea is to tune the knobs such that the output energy of the quantum state is minimized. So in the same way, a neural network is trained to minimize training error. In quantum algorithm, variational quantum circuit is trained to minimize the objective. In the case of chemistry, it's the molecular energy if the goal is to find the ground state energy. But this could also apply to optimization if the goal is to, let's say, minimize a certain function, to find a solution that minimizes a certain function. At the end of the day, it's a similar principle, except that now with quantum devices, you can afford this tunable function that is a lot more expressive, or this is uniquely expressive compared with what's possible on a classical computer. And there's a whole line of inquiry in quantum machine learning where people try to find out how to characterize the idea of quantum circuits and how to make that work.
I see you talk about quantum computing as computation of the quantum circuits, but if we maybe go back to the initial proposals of quantum computations, let's say given by Feynman, so I think he was suggesting to compute or simulate the molecules with the molecules. So do you see if there is a way of going beyond the paradigm of quantum circuitry and maybe consider like more like a quantum simulators that you can take atoms, somehow position them in the space so that would form a certain molecule and then try to measure its properties?
Conceptually, yes. In some ways, the quantum computers being built today, the gate model quantum computers, plus the quantum circuits, they are essentially trying to mimic that simulation. So the closest I have seen, I actually haven't seen, well, maybe the example from Quera years ago where they showed over 300 qubits analog simulation. I think that would be a good example. Also, I think D-Wave had some interesting demonstrations. Recently, they have this paper about computational supremacy, which is based on a different notion from the supremacy that the gate model or the boson sampling folks are talking about. In the case of D-Wave, essentially their argument is to simulate the behavior of their system, classical algorithm like quantum Monte Carlo would fall behind, will lag behind the natural sampling of their device. So there are specific simulators, analog simulators, for specific physical phenomenon. Although without too much tunability, probably this will have very limited utility. So the 300 plus example is maybe it's an Australian group. I can't remember clearly. But yeah, so it's possible to have analog simulations of a controllable quantum system for a target quantum system, but without tunable features. It's not really a computer. It's really like a model of a 747 in a wind tunnel. Right, it's a simulator of the 747, but it's different from a supercomputer that's actually calculating not only the drag of a 747, but also the drag of a race car, for instance. So I think there are definitely potential for analog simulation like that. It's really a singularly important physical phenomenon that cannot be simulated in any other ways. But without tunability, you would have a hard time qualifying that as a computer. So that's the appeal of a quantum computer, is that there's some sense of universality to it. Right? You can use it to solve chemistry problems. You can also use it to solve other problems. And that seems to be the mainstream recipe for it.
From commercialization point of view of, let's say, quantum technologies, quantum computing. So as I understand, those companies who work in the area of chemistry, like chemical products, so what are their pain points right now when they, I don't know, either design the drugs or work on fuels? So you mentioned one thing was that the accuracy of the energy levels maybe could be not enough, which leads to not the right estimates on the reaction outputs, inputs, or there is some limits in terms of which molecules they can analyze. I'm just guessing, but maybe the overall question for you would be, when you would work with those companies, what kind of pain points do you see that quantum computing could resolve or give them?
That's a great question. And that essentially was a question that we've been really trying to understand, right, in the past few years, like in different verticals. My understanding is that it's still a very, you can say, there's no clear mapping. So it is unclear, for instance, if you had a magic calculator that tells you the properties of chemistry, how would that translate into business value? In the case of drug discovery, for instance, I think many people are concerned about drug discovery these days. It's useful to calculate let's say, how a drug may bind to a target. But for an actual pharmaceutical company, drug discovery, so this calculation, binding affinity calculation, is one of the many metrics that they measure. And in many cases, these properties of potential drugs are calculated with proxy scores. So those are efficiently calculable proxy scores that allows you to quickly screen through many molecular candidates. And perhaps you can go through 1 million of those or even more. And then there are many ways to do large-scale screening and to get to a small number of molecular candidates. And computational chemistry could be one of the tools in that arsenal, but it's not the tool that will actually drive a singular improvement, because it's going to be a mixture of other tools. And for drug discovery, I think a big bottleneck is actually in making the drugs. So if you're a pharmaceutical company, I think you can keep the computer running and generate billions of molecular designs, but probably your wet lab can only afford synthesizing, a small handful of those, maybe a dozen of those for a couple of months. So there's no way you could, at least currently, there's no practical way in which you could, in real life, actually synthesize all billions of molecules and test them and see how they work. So you see that computation in this case, right, it's actually embedded in this bigger industrial workflow. And this is not only for drug discovery, but also for other industry as well. So computation is actually embedded in this bigger infrastructure. So it's harder to say that if you had this very fancy calculator that tells you, okay, yeah, this is exactly how the molecule is going to bind to the target, whether how that information translates into business value is very unclear. And I'm not dismissing the value of accurate quantum chemistry. I think it's very possible that because of insights from quantum calculation, there's a drug that gets discovered that is singularly valuable. But if that happens, it would also be because maybe the specific target that's being explored happens to be the right target, and then it happens to be that the clinical trials and all the later stages work out perfectly to the point where, in 10 years' time, this becomes $1 billion drug. So then when this does become $1 billion drug, if you retrace your steps, how much of it is actually due to the fact that there's an actual accurate quantum chemistry calculation, or maybe the credit should go to the quantum chemist that actually used the calculator to figure out the insight to discover the drug. So maybe instead of paying more dollars to the quantum computer company, you should just give the quantum chemist a raise, because so there are things like that, right? So you can I think drug discovery is a very good example because it has such a established process. And you can see exactly how a drug gets discovered and then tested, and then there's approval, and then but it's representative of the problems that you have in industry, which is that computation really happens at such a microscopic scale, where if you want to argue that it's going to change, it's going to move up the value chain and somehow create X dollars of impact, it's actually a very challenging problem.
It's like sometimes I even question whether computation is more expensive than doing the experiments directly. So it may be when they perform the wet bench chemical experiments, maybe this is when they do the quantum computation,
right?
Or quantum simulation when the molecules directly right here.